Okay.
Hi everyone, welcome back to the second week of the ZX seminar. And today we have Christine Lee, and she's from Columbia University, currently as an undergraduate student. And she's going to tell us about the joint work with Lia Yeh on constructing a qutrit quantum error correcting code with a transversal binary AND gate. And the floor is yours.
Thank you so much, Sarah. Yeah, hi everyone. I'm Christine. I'm excited to talk about this work on qutrit error correcting codes with Leah. So we're focused mainly on one specific code in this talk, but the techniques that we use can be generalized to find stabilizer codes with any logical gate. So one of the first things that we learned in the quantum computing course is that we need at least 3 qubits to do an AND gate. And this is typically implemented using the 3-qubit Toffoli gate in qubit computation. But what if we view each qubit as natively a qubit? And we'll see in the first part of this talk that we can actually perform an AND gate using just 2 qutrits. And we'll show how to do this and then also construct an error correcting code that has this logical gate. And this has a little bit more motivation. Why do we care about qtrits? So higher dimensional systems, like qtrit, a 3-dimensional system, has advantages over qubits, a 2-level system. So we have a larger local Hilbert space that can give us more efficient algorithms and circuit compilation. And in particular, qutrits can be used to efficiently emulate qubit gates, where we kind of focus on the qubit subspace of the computation. And also, hardwares like native superconducting, trap down, natively have more than 2 levels. And lastly, error correct QEC codes in higher dimensions can have better code parameters, and then it's possible for qubits. And if we use qtrit codes to emulate qubit computation, then we can also suppress qubit leakage errors to the Ket2 state. Um, yeah, okay, so just a little bit more background on qtrit computation. So we have in the 3-level system 3 basis states, Ket 0, 1, 2. And the poly X and Z generalize into a shift and clock operators. And notice that they're no longer self-adjoint. And then there's 2 different types of control gates that we use in this talk. So the first is the CX gate. And this is sometimes also known as a lambda control X. And this is Clifford. And the second is the ket 0 controlled Z, which applies the Z if only if the control qtrit is a 0, and this is not Clifford. So in combining the Clifford group with the non-Clifford, we can get with a T gate. We can also get and we can get universal computation. So kind of this work began by looking for a way to implement the AND gate using qtrits. And we can use this using what we call emulation, which is when you focus on the behavior of the first 2 levels to match that of like a qubit's computation. But the third level is left unconstrained. So in this example, you can see if we don't disregard like basically the additional rows of the truth table for the circuit. So this is a circuit for the AND gate using qtrits and to emulate it. But for and as kind of further motivation for why we care about the AND gate in particular. So you can see that any classical binary classical binary gate can be emulated fault tolerantly using qtrit Clifford+T gates without ancillas on the left here. It kind of has this like binary tree structure like recursively using the circuit from the last slide. And also notice that an n-ary and the generalized Toffoli gate takes n qutrits, and this saves on circuit width compared to qubit implementations. And the generalized qubit Toffoli gates, so any n-qubit controlled X can be implemented unitarily without ancilla in qutrit Clifford+T in log n depth. So if we have a code that can do this gate, it can give us also a more efficient way to do logical qubit computation. Yeah, okay, so kind of going back to this circuit that we have for for emulating the AND gate, what we want in the code is, as you see later, is that we want a symmetric circuit that implements a certain gate. And so we manipulated the circuit a bit to find this symmetric version of the circuit that also emulates the AND gate. Okay, so kind of now I kind of want to jump to the idea of like going from the symmetric circuit to a code. And the inspiration for this comes from the going from the qubit CCZ like symmetric circuit to the 832 color code. And this kind of ties into the idea of exact circuit synthesis as a way of finding transversal gates in a QEC code. So I got kind of a lot of work in QEC focuses on finding good codes, but it's often hard to figure out what are the transversal gates of a code. So we kind of were thinking, what if we go the other way? What if we find a code with kind of a known transversal gate, or like starting with a transversal gate implementation from a symmetric circuit synthesis, and then constructing a code around that. So this kind of inspiration comes from the 832 code, which is an error correcting code that encodes 8 physical qubits into 3 logical qubits with code distance 2. The kind of encoder can be visualized on this cube structure. And what's interesting about this code is that it has a transversal implementation of the CCZ gate, which is non-Clifford, and this is implemented by applying T or T dagger gates on the physical qubits. So kind of like the 8 corners of the cube in the visualization. And this is transversal, which is really nice because it prevents errors from spreading within like the code block. Yeah, and then just another tidbit on like the code distance is the minimum weight of a logical operator. So we want higher code distances because it protects against more possible errors. So distance 1 is essentially kind of a useless code. And starting from distance 2, we can detect and so forth. Yeah, okay, so that was the 832 code, and it has the symmetric CCZ gate, right? So now, alternatively, we can start from the CCZ gate and a symmetric T-depth 1 circuit that implements that gate. So this is such a circuit. This is from Selinger's paper, and you can see that we can split this circuit into basically 2 halves. So the first half can view as kind of an encoding um, the encoder, right? And it's a fully like C0 circuit, and C0 circuit is a CSS code. Um, and then the middle part with the T transversal T gates, that is the physical implementation of like the logical circuit that this overall implements. And then on the right side, we have the ideal decoder. So if we look at this as a code, right, then we find that the code described by the encoder, so E, is a 731 code. And then if we add a weight 8 X-type stabilizer, so kind of this is like kind of at the bottom here, like representing this in ZX. So the weight 8 is represented by the green spider connected to all 8 uh red spiders on all 8 legs of um and then fuse, and we can see that adding this additional stabilizer increases the code distance to 2. And this gives us exactly the 832 code. And this idea was mentioned in a blog post by Earl Campbell called "The Smallest Interesting Color Code." So in this case, also one thing to note is that it just so happens that like adding this X-type stabilizer maintains the logical gate implemented by this circuit. But in general, like it's not true that if you just add any stabilizer, the logical gate is preserved. So and we'll see that we'll have to do some extra work to make sure that the logical gate um, that we wanted to implement in the first place is preserved when we add stabilizers to increase code distance. Yeah. So yeah, I guess like um feel free to stop me at any point also, like if there's any questions. Yeah. Okay, so we kind of saw how to go
I have a
the
question.
yeah.
So before, like about, I think it's around bullet point one, you're talking about, you like to find a symmetric T depth one circuit, and here, why do you like in terms of the AND gate, the qutrit AND gate implementation? What is the motivation of having a symmetric circuit versus any kind of circuit?
Mm. Yeah, so I think so having a symmetric circuit gives us this kind of natural way of like looking at it as a code. In particular, we want um a, a a a circuit that kind of has a C naught like inner portion, right? Um and and that's because if we can like take so there's this idea of like looking at the first half as like an encoder, and then the other like kind of half of the symmetry as like an ideal decoder. And in this form, then like the kind of the middle of the middle section of like the symmetric circuit, then is the physical implementation um of a of so overall the circuit implements some logical gate, and then the middle portion gives us a physical um implementation of that. And I think it's like it's a nice way of like I guess like starting to like construct a code that has a given logical gate, if that makes sense. So like if we have a binary and um like a symmetric circuit for the binary and, then we can do something similar to what we saw here with the CCZ, but like going from CCZ symmetric circuit on this slide to a code that has this gate as a transversally implements this gate. Um, so we kind of wanted to do something similar with the binary AND gate. So if we have a symmetric circuit for it, then maybe can add stabilizers to then construct a code that has a transversal implementation of that. Does that make
Yeah,
sense?
Can I think of it as because when we're trying to find the fault-tolerant implementation of a logical gate, the multi-control gate are always difficult to find. Like by fault-tolerant, I mean the transversal implementation. So you kind of start from the other end. You say, well, like we know in literature, this is how people implement a multiply controlled gate. Then what code does it correspond to? Then when we look at this code, it automatically has the transversal implementation of the more difficult gate.
Yeah, yeah, exactly, exactly.
So sorry, like
Mhm.
this detects zero errors and corrects zero errors. This code. So is it really fault tolerant?
Um, Wait, sorry.
So it's a
Uh,
distance one code. So it
yes,
corrects no errors and it detects no errors.
yes.
How is this fault tolerant by that
Mhm.
definition? Right.
Yeah, okay, that's a good question. Okay, so we're saying that we first like kind of have the circuit, right, that implements this uh logical gate transversely, but it is distance one. But what we have to do is to add stabilizers to it that first preserves this logical gate and second increases the codistance. And this is kind of not a non-trivial process. Um, and there are kind of different ways we like explored doing this. In this case, like uh the okay, so this is a 731 distance one code, right? But if we add a full weight X type, just one X type stabilizer that checks so add an N11 and then checks all 8 qubits, then this increases the code distance while also preserving the overall like, logical gate. So it still has this uh transversal CCZ. And that is like the kind of I guess fault tolerant implementation, right? I think like what I'm trying to say is that when we have a symmetric um circuit um for a given logical gate, we can first kind of just look at it like a shift in perspective and look at it as a distance one code, and then try to add stabilizers to that um to increase code distance. Does that make
I,
sense?
but that's not always guaranteed. It's,
Yeah, no, it is not. Definitely not. And we'll kind of see like in this case, like for the CCZ gate, like going from that to the 832 code, it works out nicely that the logical is preserved. But first, it's like what stabilizer do you add to like increase code distance is kind of tricky. But and then also like to make sure that the logical gate is preserved. We'll kind of see like that in how we increase the code distance for the binary and
so,
case.
so, so in
Yeah.
this case, you're relying on post selection after you get to the 832. Is that right? Because there's a distance too, so it's still have
Mm,
to post select, right? You still have to can't really
yeah,
code any
yeah,
errors.
yeah. Um, yeah, and I guess like that's so I guess the main kind of work so this is kind of like inspiration, but like yeah, the code
Okay.
that we have so far is also just like increased to distance two, so definitely like a future um direction like is increasing the code distance further to distance three, maybe by adding additional stabilizers.
So the
Yeah.
maximum you can really add is two more, right?
Yeah. uh
Because of dimension
yeah.
arguments.
As yeah.
Okay.
Um
Yeah, thank you.
mhm, of course.
So, just to follow up a little bit, what is the necessary condition that when you add the stabilizers, your logical are preserved? Like, what do you need to satisfy in order to still have the transversal implementation of a CCZ gate in the 832 code?
Mm, this is a really good question. So in this case, in the qubit case, like um you can represent these using spider nests and like uh adding kind of a weight a X type stabilizer kind of preserves like it's sort of like adding a spider nest identity that preserves the logical. In the qtrits case, it was less clear because we don't know like a spider nest identities. So we tried that, but that part like is kind of, it didn't quite work, so we kind of tried addition like other methods, and it was kind of a trial and error process. So in general, we don't have like a for qtrits like there's not really like a rule book for like adding stabilizers that preserve logical. So that's definitely also something that like we're thinking of. Um, if there's kind of a more straightforward like rules for this. Yeah.
Thank
hmm Okay. Cool. Okay, so now I'll talk about like kind of how we use this idea from the transversal CCZ gate and the 832 code to the transversal AND gate and the qtrit code, starting with a distance 3 to 1 code. Yeah, okay. Um kind of a key ingredient in this symmetric circuit I'll present first is this ket zero controlled Z gate. Um, and there's a symmetric circuit implementation already from this Microsoft paper from a few years ago. And as I was talking about earlier, we only found the symmetric circuit for the AND gate. It has this ket zero controlled Z in the middle, so we can kind of combine these circuits, and then we'll get an overall symmetric T T depth 1 circuit for the AND gate. And so kind of taking the same idea of looking at the first half as an encoder, and then we have the 3 T gates as a physical implementation of the physical like transversal implementation. And then we can kind of figure out like what is this code. So okay, yeah. I guess I kind of this part will use more qtrit ZX calculus, so I'll take a second to give a quick intro in case people are not familiar. So this is very similar to the qubit ZX calculus, except now okay, so, you'll notice like the spiders have 2 phases represent yeah, for kind of the ket 1 and ket 2, or for ket omega and omega conjugate, so in the x spaces. And then the other thing is that in the qtrit ZX calculus, it's no longer only connectivity matters, so the directionality does matter. It's see on the bottom here. This is so the left side of that's a CX gate, so green first and then red. And that's not the same as like a CX like dagger, which we flip the direction. Or we'll need to add a dualizer when we flip the direction. And and then also like applying a CX gate twice gets us the dagger. Yeah.
Chris,
Yeah.
how the definition of this two linear map, are you using A and alpha interchangeably and B and beta interchangeably?
Oh, yes. Thank you. All right, I didn't catch that. Yes. Um, and then yeah, here are the rewrite rules. So yeah, these are taken from Townsend Teague's paper. So yeah, we'll mainly use, I guess, like fusion and strong complementarity in some of the rewrites here. Yeah, okay, so before this, we were talking about this symmetric circuit, symmetric T-depth 1 circuit for the AND gate. So here it is, and then we'll find the ZX diagram representation. And in particular for the inner portion of the code, which implements the zero control Z. This is like an entirely C0 a CX plus T circuit, and so we kind of focus on this as the inner like CSS portion of the code. And then another kind of so another result that like is gonna be useful is we take this inner portion of this CSS portion and we can actually it forms a phase gadget. So this is gonna be a kind of a useful ingredient in the next part when we kind of try to increase code distance. So we can rewrite using this phase gadget rule. It's around complementarity. We'll go through the details, but essentially you can rewrite the zero control Z in this form. Okay, and then from the symmetric circuit representation, right, we can rewrite that into the normal form. So in the top row here, this is the first equal, the symmetric circuit to the right of the first equal sign. It's taking the left half of that. And then we can get the XZ or the ZX normal forms, which gives us a way to directly read off the stabilizers based on the connectivity of the map. And we'll see that this has a overall distance one because one of the Z stabilizers has weight 1. So also there's no X-type stabilizers. So yeah, overall this is a 3-2-1 code, and then the question now is how do we increase the code distance by adding stabilizers while maintaining the logical. So next, well, it's kind of talk about that. So as you may remember, like this code, it doesn't have a X-type stabilizer. So kind of taking the idea from the 832 code, we can add a full how that was formed by adding a full weight X-type stabilizer. We can kind of try to do the same thing here. And we'll see that if we do this, push it out, and then get the push out the inner like red spiders. This is this circuit, so it's zero control Z conjugated by these CX gates, but this actually changes the logical. It's no longer zero control Z when you conjugate with an ancilla. So now the question is like how to kind of go back to how to preserve the logical, right? Okay, so what is this circuit? You can kind of we observe that this you can expand this circuit into or as a multiply controlled like phase gates. If you break down kind of the plus state into the 3 let's consider them as 3 cases, right? In 0 case, like you don't change anything. For 1, then you apply the X gate once to the second wire, and then this applies an additional omega. If it's a cut 2, you apply X twice, and then you apply omega twice. So you can kind of write it in this form. And then if you kind of just look at the middle portion of this, so ignoring the ancillas, ignoring the initialization post-selection, it's true like that if you can expand out and then reorder the Z and the omega and what you'll see that is equivalent to two zero-controlled Z gates applied to the second and third qubits. And then also in lemma 4, this is also equivalent to the zero-controlled Z conjugated by CX gates. And we'll kind of use this in the next step to get back the logical zero-controlled Z. So we have this new circuit that preserves this logical, but also increases the codistance, right? Because we want the CX conjugated circuit. So we first we wanted this double zero-controlled Z, one to the original one and then one to like an ancilla. But to preserve it, we apply the zero-controlled Z dagger. And then using kind of the previous lemma, we can see that this left portion with the two zero-controlled Z's is equivalent to one of them conjugated by the CX gates. And then the control part of the CX dagger commutes with the Z dagger. So then we end up with an overall circuit that has these CX conjugation, so increasing codistance, but also it maintains the logical zero-controlled Z.
Sorry, Christine, pardon my memory. Are you saying that the controlled X with its dagger is giving us a stabilizer of X type?
Control, sorry.
Like this
Yeah.
conjugation.
Yes. So because this comes from here, so like we're adding a full weight X type stabilizer. So we can kind of represent that in the symmetric circuit by like it's like the green spider with red spider legs on like all three qubits, and then like when we push that out, like becomes the CX gate like conjugates. And this you can see that like this increases like the Z distance, like because like if you pass in like Z, like then it wouldn't like commute through because it has this stabilizer that checks it. Yeah, so I had noticed like from here, I guess we could just like notice that when we have this CX like and CX dagger conjugating the circuit, this increases like the Z distance. Like when it's only like Z distance one, then it increases the Z distance.
Right, I guess I'm confused because
Mm.
the stabilizers showing above has supports on all of the physical qutrits, but the control gate below does not have the
Mm.
support on the top wire. So I just wonder why you would say the bottom one correspond to the stabilizers above, or you actually push the stabilizer leftward in the circuit, so you actually reduce the number of support.
Mm. Um, yeah. I think okay, so I think like here we also I think we use like additional rewrites like um let's see. Um Mm, yeah, I think we did some like after like some rewriting, like we this ends up being just supported on the the second the second like physical or the second qutrit. Um yeah, I guess like if you expand out like the zero controlled Z like with the symmetric form, then and then you can rewrite it to so that the support is on all it's on I guess all three of the physical um qutrits. Yeah, I think this just came from like rewriting and then like putting in like replacing uh the middle part with the zero controlled Z like um yeah, but it is still like supported on all three, like even if it's like this bottom like kind of representation, like if you like replace it with a full circuit and then rewrite it, it's like still supported on the all the physical qutrits.
Thanks.
Yeah. Um yeah, okay. So we kind of so we ended up with this circuit on the right here, which um kind of maintains that C CX gate conjugation and implements the zero controlled Z um gate. So kind of using the previous result that like the zero control Z has this phase gadget form, we can replace that here. And rewriting the whole diagram in ZX using ZX calculus to a combined phase gadget. Um, then we can turn this into a symmetric form. I mean, we can notice this by matching connectivity of the phase gadgets or from some overpass or by rewriting. Yeah. So, and then from here, then we can expand this into a full symmetric T-depth one circuit. And this will end up with 6 physical qutrits. So okay, so just to recap, we went from this new circuit for the zero control Z with the CX gate conjugation. Using phase gadgets and rewriting, we end up with the full symmetric T-depth one circuit. And yeah, so okay, so looking at the first half, right, as the encoder, then we can like you look at the normal form and get the stabilizers from connectivity. And this we checked code distance is overall code distance 2. So it is a 622 code. Um, and yeah, I guess in particular, kind of adding that like full weight X-type stabilizer increases a Z distance. And then lastly, like one kind of additional thing that we can do is what we call qubit subspace projection. So kind of the idea is like we want to use this code to like if we wanted to use it for qubit emulation and computation, right? We want to be able to detect if a logical qutrit emulating a qubit has sort of entered this Ket2 subspace. And we can use this gadget kind of at the top here to check for when a logical qutrit is in the Ket2 subspace. And we can combine this with the code to get a way to do error corrected like computation emulating qubits using qutrits. And this is kind of ongoing work, and we're kind of looking at creating a code around this gadget as well, and possibly concatenating that with the original code. Yeah. So okay. Oh. Yeah. Any questions so far? I'll like wrap up. Right. Yeah. Okay. So in summary, the kind of a main idea is that we can view a symmetric T depth one circuit as a stabilizer code. And in this work, we combine this idea with idea of emulating qubit computation efficiently using qutrits. And we demonstrated this in the example of the 622 code, which has a transversal AND gate. Some other things that we're looking at is, well, first finding other logical operations of this code. We know like that, it has the AND gate, but it doesn't have, for example, a Hadamard gate. So it's like, what else can we combine it with to get universal computation? And then we're also like looking at simulating this, and possibly like looking at extending this idea of exact synthesis, T-depth1, symmetric T-depth1 circuits, to other codes with good logical operators. Yeah, so I think that's everything. Thanks.
Thank you, Christine, for the very interesting talk. Does anyone have questions for Christine? Leah.
Oh, yeah.
Hi, this is Razin, not Leah.
Sorry, my laptop got robbed.
Um, so I have a question based on the last slide that you showed.
Yeah.
Yeah. So here you talk about this qubit subspace projection, and how you can project some of the qutrits. Like, can you define a code which goes from, let's say, 2 qubits to some qubits and qutrits? So it's like
Oh.
Yeah.
Like going from only qubits to qutrit?
Only qubits to some qubits and some qutrits on the physical level. Or yeah.
Wait, okay, so at the physical
Sorry.
level,
Some a qutrit and a qubit at the logical level to all qutrits at the physical level.
oh, I see.
Yes.
I think yeah, I think that's reasonable to think that like maybe for a portion of the logical qtrits, you care about all three levels, and then for another portion you care only about the first two levels.
Yeah, I would imagine, like, based on the bottom left diagram you have here, that the logical qubit is the thing you do the operation on, and the logical qubit is the thing that's carrying the extra information to make it ancilla free. And
Yeah.
yeah.
So I can say a bit about that. So this projector onto the code space, onto the qubit subspace, this pi sub l, in the case where you have a code going from a qubit to qutrit, since the projector is equal to e dagger followed by e, where e is the encoder, then this pi sub l is the projector onto the code space for when you're encoding a qubit into the 0, 1 subspace of the qutrit. So this top thing, this is the code that Rosine is referring to. So this is your maybe you would see it as the and we sometimes use this notation for when we're writing these ZX diagrams. The mixed dimensional ZX calculus, this is the one input, one output green spider that it's 1, 1, 0, like it's identity on ket 0 and ket 1, and then it annihilates ket 2. So that's what this pi sub l is.
Mhm.
Thank you.
So in
Thanks.
short, the answer is yes, and it is this slide.
I also have a question. So earlier, when you showed the qutrit ZX diagram, there are a lot of the places where the Z and X spiders has two connectivity instead of one. And we know in qubit land we can use half rule to remove them. And here, could you remove them?
Oh, that's a good question. So, we cannot remove them because in qutrit ZX calculus, like, if you have 3 wires, if you have green, red, and 3 wires connecting them, then you can remove them. So it's like mod 3. When we have 2, it's actually I guess for example, like if in the bottom kind of expanded out like circuit form, when you have 2, that's like the CX dagger. So it's not self-adjoint. So you have to apply it's like kind of the idea that like if you apply CX gate twice, that gives you the dagger. So the 2 wires is like applying that twice, and that's equivalent to the dagger.
Right. And another thing that you mentioned is that in qutrit, you no longer have OCM. And when we're doing the pushing through the encoder, having OCM is actually very important because it allows us to manipulate the diagram wherever we want. Then
Yeah.
if we generalize this work to pushing through the encoder, how would you handle not having OCM in the qutrit land?
Also a question. I think like yeah, it definitely makes it more tricky. It's like um I think we're still like figuring out as how to kind of generally handle not having like OCM for like adding stabilizers, right, and rewriting. I think in this case, like we were able to use this phase gadget rule. For example, here like kind of a tricky part was like handling the CX dagger on the right side. It has like a different direction than the phase gadget, right? But we happen to like there happened to be, right, like this qutrit phase gadget rule. That was from earlier, sorry. Okay, I won't go back. But basically like replacing um this CX conjugate like with the additional like CX gate with and turn that into a phase gadget form. So but that uses strong complementarity kind of as um to I guess like change the direction to match. But yeah, I think like it works out here. But yeah, it does make it trickier for rewriting in general.
Thanks.
Hi. On your last slide, you mentioned something about having a threshold. What families of codes are these? And is there indication what? So why is
Yeah.
indication that there is a threshold? Or is it just like a something that you conjectured?
Yeah, this is very much a conjecture. I think like we'll have that like for finding a pseudo threshold, like it's kind of an open question of like what other codes maybe by further
So,
for
so do
like
you, do
further
you have
adding.
like a family of codes in mind, or is it because in order to have a threshold, or even to have not a pseudo threshold, but a threshold, you
Yeah.
need family, right? You need a scaling parameter.
Yeah. Yeah.
So does this work with on some families of codes, or is it? Yeah, I'm just curious to know.
Yeah, I think we don't know yet. So we haven't like tried this like fully with like more code, so that's definitely like still future open an open question. But I guess just like that's something that would be interesting to explore. Just like I kind of mentioned there. Um, yeah, I guess yeah,
Okay.
yeah.
And have you also looked into Cody Jones' thesis, like a dissertation, like his PhD dissertation? There's a bunch of
Oh,
circuits here that look quite similar, but subtracting the qutrit interpretation in Cody Jones. So,
I think the name sounds familiar. I don't remember. Hmm. Okay, I don't think I have actually.
don't worry about it. Yeah, thank
Yeah.
you.
Okay, thank you for bringing this up. I'll definitely look into it.
If I can just give a quick comment on the concatenation. So because this is a distance 2 code, we wouldn't concatenate it naively, like with itself.
Mhm.
But because it happens that the transversal physical operations are T and T dagger gates, the simulation we had in mind was that we could simulate concatenating codes that have transversal qtrit T gates. Those do admit thresholds, and then using those, what would be the corresponding like cost of on top of that do a 622 code at the very end. So to transform what is the transversal logical gate from T to this qtrit binary and or qtrit kit 0 controlled Z.
So sorry. So you mean that your intention is to concatenate it? Is that right?
So yeah, so because the physical transversal gates here is that for this code that we have is 3T and 3T dagger gates. So it is compatible with just concatenating with codes that have transversal qtrit T gates. Those have thresholds. So that then the question is now, what is the actual noise? What is the noise under different noise models? How does the code perform?
I see. Thank you.
If no one so let me ask another question about the um, fault-tolerant implementation. Um, is it possible to start with a circuit that has transversal implementation of Clifford's, since we know that there exists qubit with Mueller codes to do magic state injection, so you could actually get fault-tolerant non-Clifford gates. And if you start with that circuit, could you get some interesting qutrit error correcting codes?
That definitely seems possible. Yeah, we haven't looked into like Clifford, transversal Clifford gates yet, but yeah, I don't see why not. Like, yeah. as long as it, I guess, like there's some qutrit symmetric circuit implementation of that gate, then we can try to add stabilizers and yeah, so try to get a transversal gate in that code with that.
Thanks.